35 minutes, something like this, and then some time for question and answer.
Okay, it's 9:15. Hello everyone, good morning, and welcome to the Machine Learning Coffee Seminar. Today we have Professor Esa Olvila from the Department of Electrical Engineering, and he will describe for us how to estimate high-dimensional covariance matrices. Please.
Thank you. So thank you for this opportunity to speak here. It's my first time, even though I'm quite close by at the third floor of this building, but very nice to be here. Before we start on the topic, I would like to advertise a little bit about a new book that just came out in November. I received these hard copies just 2 weeks ago, so if you are interested, this is about machine learning for signal processing with basically additional twist is that we want our methods to be robust, so they should be tolerant to outliers or Gaussianity and stuff like that. So I just put it here. If anybody's interested, then please browse it. So it also covers a little bit of the topic that I'm going to talk today, so the covariance estimation. And we have toolbox also, MATLAB toolbox at the GitHub, so anybody who's interested, you can go. Those codes are free to use. You can just go and start using them. So the covariance estimation problem that I'm going to talk today is as follows. So we have random vector x, which is p-dimensional, and we think that this p, so the dimension can be large. And we have basically n samples, so IID realizations from that distribution. And we would like to estimate the covariance matrix sigma, which is symmetric and positive definite matrix. And the most commonly used estimator for this parameter is, of course, the sample covariance matrix, and it has various nice properties. We know that it's a maximum likelihood estimator for the Gaussian distribution, and it's also unbiased estimator. So those are the good properties of that. But in this talk, I'm going to concentrate on the case that we have sample size is small compared to the dimension, which is very large. And in that case, of course, the problem is that our estimator S here is not going to be invertible, so it's not going to be positive definite. So obviously, it's not very proper estimator in this case. So something has to be done. On the other hand, in many applications, I will show you the applications, for example, that the data itself is not going to be Gaussian. So it's not going to be, so what I'm trying to do in this talk is to say that in the case that your P is large, N is small, you have non-Gaussian data, you can do much better than using this estimator here. So why covariance estimation? Well, I'm going to talk about the top problems, so the first two there. But if you're, every one of us has sometimes done PCA, so you estimate the covariance matrix and the eigenvectors. You project your data on these eigenvectors. So you have to estimate the covariance matrix. If you do radar detection, which we do in signal processing all the time, we need to, our optimal detector usually depends on the covariance matrix. And if you do graphical models, you need to estimate the covariance matrix. So there are multiple applications that you actually need the covariance estimator. So to put this talk into the right context, I want to talk a little bit about bias variance trade-off. So if we have any estimator, we often want the estimator to have a small mean-squared error. And now, since we have our estimator is a matrix, we use a Frobenius metric. So here, as defined there, and we can decompose the mean-squared error as the variance of the estimator plus the bias squared. And good thing that we know about, or a good property that we know about the sample covariance matrix, that it's unbiased. So in fact, the mean-squared error is just this variance part. But the problem is that, of course, since n is quite similar to p, that its variance is going to be very large. This is also a fact that is known by Marsenko-Pasteur law, that the sample covariance matrix is very bad estimator of the true covariance in that case. So what one usually does in this case is that you introduce some prior information. So if you're a Bayesian, you probably introduce some prior distribution on your parameter. And you probably shrink that estimator, so the sample covariance matrix, towards that prior structure, so the prior matrix, which is positive definite. And then how much you pull it towards that structure is controlled by this parameter beta. And that is the parameter that we want to find. So how to find that optimal parameter so that we, in a proper way, pull that estimator towards that prior structure. So this is very popular estimator by Leroy and Wolf. And it's such that you pull your sample covariance matrix towards a scaled identity matrix. And there's a tuning parameter beta, so how much do you pull? So you can think of that as a degree of belief, how much you trust the sample covariance matrix. So when you are completely believing in your sample covariance matrix, then beta is 1. And then, of course, when we are here in the case that P is similar to N, so the dimension is similar to the sample size, you want to pull always at least a little bit towards that identity so that your estimator is always positive definite. And ideally, we would like to have that estimator there has the smallest mean squared error possible. So for different beta, we have a different mean squared error. So for example, for this beta, we would obtain this mean squared error. For this beta, this, and so on. But optimally, we would like to choose this beta. So we get the minimum of this mean squared error. So this is the normalized mean squared error. And this is our estimators. We propose 2 estimators. As you can see, this is the optimal value. We really get close by to that. And this is also another one that we propose. And we get close by to this curve. So to the bottom of the mean squared error. And this is the estimator that was originally proposed by Leroy and Wolf. So they also try to estimate that beta. But as you can see, you are quite far off from the bottom. So why do we gain this? We exploit the fact that data can come from some underlying distribution. And the distribution family that we assume is very large family of distributions. So we are not making very strict parametric assumptions to do this. And this is the references of this talk. This is a joint work with 2 of my doctoral students who are sitting here, Elias and Tabassum. And we have also codes available. So MATLAB Toolbox, you can go and download it and just use. We have also these examples that I show. We have it also there in the toolboxes. So we have a pretty nice 4-course menu for this morning. I hope your stomach is not full with the porridge. So I'm going to first talk about this application in finance where you need the covariance estimator. So this is a mathematical framework that was put by Harry Markowitz in 1952, but it was further developed by James Doblin and William Sharp and Eugene Fama. And probably the Sharp is the most well-known for just a common man because the Sharp ratio, you see it when you open the newspaper. You see each stock has a certain Sharp ratio. So all these guys that I just mentioned are Nobel Prize recipients. So this is a very important topic in mathematical finance. But in order to use this theory, you need to estimate the mean of the returns and also the covariance matrix of these returns. And the problem is that you have a large set of assets in your portfolio, but you don't have a historical return that you have is quite limited because you don't want to look too far to the past, and that is the problem. Of course, you have lots and lots of available data, but it doesn't make sense to look too far in the past. So what is the portfolio? It's basically, it consists of stocks, market indexes, government bonds, corporate bonds, currencies, and so on. So there's a lot of stuff in the portfolio. And we have P assets in the portfolio, and we have a certain amount of money that we want to allocate to these assets. And these weights are the fractions that we want to allocate to each asset. And they sum to 1. So we allocate all our wealth. And then we have net returns for each asset. And we can compose that net returns of each asset into this p-dimensional vector. And what we are interested in this portfolio net return. So what is the return of that portfolio? How well did we do? So essentially you would like to have, if we have a large positive net return, we would like to have that weight to be large so that we make a lot of return. On the other hand, if we have a negative return, so we would like that fraction of that wealth to be negative when we make a short position on that asset. So what you do is that you have historical returns, and then you estimate the mean and the covariance matrix using that data. So people do this kind of simplifying assumption that, okay, so one has to assume something and pretend that it's true. So we have the historical returns, and we estimate the mean and the covariance matrix from that data. And two important statistics that we look is the mean return of the portfolio and the risk of the portfolio, which is the variance of that portfolio return. And in finance, the standard deviation is called the volatility. So and the variance of the return is the risk. So those are the terminology in finance. And there's a multitude of allocation strategy in finance. How would you allocate? How would you choose those weight vectors, actually the weight vectors, or the elements of that? So a very conservative strategy is that you just want to minimize the risk. So you want to have a portfolio that have very small risk, so small variation, so that there's a small chance to make huge losses, but small chance to make big wins either. So it's basically very conservative strategy, but let's just look at this example here, just for simplicity. So this is the optimization problem, and it has a unique solution given there. And as you can see, in order to use this strategy, you would need to estimate this covariance matrix of the net returns. So we can look at some indexes here. For example, S&P 500 and NASDAQ 100. And you can see that in 2017, the stock markets were very steady. They were steeply rising in general. There's a certain very steep trend there. And then if we look the daily net returns, you can see that there's fluctuation there. For example, NASDAQ 100 is more volatile than the S&P 500, and this is because it contains a lot of technology stocks, and those are more. There's more fluctuation in technology stocks because they tend to rise more steeply, but they can come down. Quite often, somebody, maybe Zuckerberg or some other guy said, Elon Musk says something. They do bad decision, the stock goes down a lot. So there you can see that there's sometimes you can make quite big loss. Sometimes you can make a big win here if you do smartly. And so the question is that if is the stock data or the returns, this historical data, is it Gaussian? And you can see that it's actually not really Gaussian, it's more concentrated on the mean. And there's also heavier tails. So in fact, there's far more concentration on the mean, and on the other hand, there's a more concentration on the tails than what Gaussian theory would say. So this is actually a very good example of heavy-tailed distribution. So something that robust statistics is looking at. So this is the Gaussian, but here you can see that there's far more probable to be on the center and on the other hand on the tails. And also why this phenomenon is happening is there's also some other tricky things happening. For example, sometimes the machine learning algorithms are not working well, and that's why there's a big fluctuations in the stock market. So this is an example in 2017, 9th of June. Technology stocks dropped because the machine learning algorithm did funny stuff. And I think it's kind of started at this kind of butterfly effect. So the other algorithms started to look, they noticed that something is happening, technology stocks are going down, and so the stock market on these stocks went down a lot, just in one day, but of course they rise again quite soon. And then on the other hand, there are other stuff happening in stocks. There are very influential people. Donald Trump tweeted just 10 days ago that we are doing well with China, everything is cool. And that, of course, affected. So he tweeted that when the stock market had already closed. But the next day when it opened, the investors had, I'm sure they follow his tweets, and they start to think that we should invest. And then just to look this in practice, we have a real stock data here. We have 45 stocks from Hong Kong, Hang Seng Index. And that's the year that stock markets was not so stable as it is nowadays, 2010, 2011. And then we have 400 stocks from S&P 500. And we use the sliding window method, so we invest our money on these 400 stocks, for example, here, using this very conservative global minimum variance allocation strategy. But we use the sliding window method, so we use n previous days to estimate the sigma, and that gives the weight vector. So then, of course, we can look like, then we allocate, we keep our portfolio for 20 days, so about 20 trading days, so about 1 month. And then we compute what are our returns. And then after 1 month, we update our portfolio again, and then we allocate our wealth again to these different assets. And we do this repeatedly until we are at the end of the period. And then we can look how well, since the idea was to minimize the risk, we can look how well did we do. So we can look how well our covariance estimator did in minimizing the risk. And you can see here that this is the annualized, so this is like a realized risk. So there's a theoretical risk, but what was the realized risk? So here you can see that our estimators, which are the red and blue, and this is the conventional Ledoux-Wolff estimator, we are doing better in minimizing the risk. So we are doing, what the theory says, we are doing better with our estimator, which kind of takes into account the fact that data may come from elliptical distribution. But the other estimator doesn't make any parametric assumptions on the distribution. So it looks like we gain something with this assumption that is made. And you can also see that our estimator and Ledoux-Wolff estimator are doing the same thing. So we estimate that shrinkage factor, beta. And you can see that, so this is the window length, so how much historical past we use to estimate the covariance matrix. And you can see that Ledoux-Wolff estimator has more belief in the sample covariance matrix than we have. We have less trust on the sample covariance matrix, and we put more emphasis on the on that prior. And you can see that this is the also when the stock market was more turbulent, there's also more risk. You can see that the risk is higher. The realized risk is higher in that year than it is in this year. And also it depends on what is the good amount of historical data that you would need. You would look into the past less than in here. Here you can use more historical data. You can use even 200 past daily returns. So let's talk about what these estimators then are built. Is the following. So you look at the following combination of the sample covariance matrix with the identity, and you would like to find those weights optimally. So that beta and alpha, so that your estimator has the smallest mean squared error, as small mean squared error as possible. So this is a very simple idea. This is basically came up by James Stein in 1950s. I think he was looking at the location problem. But you can, of course, use this in other cases. So, but of course, if you solve that problem, then these weights will depend on the unknown covariance matrix. So it will not be much help, because those are kind of oracle values which you cannot use because they depend on the unknown parameter. And this problem was solved by Edouard Wolff in their original paper. And then Chen and co-workers improved it in the sense that they assume that the data is from Gaussian distribution. And of course, if that holds true, then you can do much better in estimating those, how much you put these weights. But here the idea is that we don't want to make that assumption on the data, because Gaussianity is something that nobody really believes in. But now we say that the data comes from elliptical distribution, so it includes t distribution and other distributions like that. So we need some statistics. One of them is this mean of the eigenvalues, which I denote by eta. And the other statistic on the covariance matrix is the sphericity measure, which measures like how spherical is the covariance matrix. So spherical covariance matrix is proportional to identity matrix. So it's equal to 1 when that assumption holds, and then it's upper bounded by the dimension of the data. So this is a sphericity statistic. So it's basically mean of the squared eigenvalues divided by the mean of the eigenvalues squared. And so we wanted to find those beta naught and alpha naught, and it turns out that they depend on these two statistics that I just showed you. So the mean of the eigenvalues and the sphericity. And here you have the sphericity, and here on alpha naught you have the mean of the eigenvalues. And the good news is that we can just plug in, if we can find estimate of beta, we have an estimate of alpha. So we can just basically, we have just one tuning parameter in this problem, and that's beta. So that's a good news, because now we have only one tuning parameter. So we only need to find that beta and just shrink that optimally towards this scaled identity matrix, where the scale term is basically determined by this mean of the eigenvalues. So the parametric assumption that we make is that the data comes from elliptical family. And you probably know some elliptical distributions or members in this family, even if you have never heard of elliptical distribution. Because maybe if you're a Bayesian, you probably know t distribution or inverse Gaussian, multivariate inverse Gaussian, or any of those. And they all belong to this family. And it's basically the family is parameterized by the mean and the covariance matrix. And then there's this density generator which tells then, so if we have Gaussian, we have a certain form for that density generator. And what we assume is basically that only thing that we assume that the data comes from this large family, but we don't specify the exact distribution. So we are not saying that it's Gaussian or D-distribution. And we assume that the finite fourth order moments. And we also need elliptical kurtosis parameter, which is basically a generalization of the kurtosis to elliptical, to this kind of distribution with, which is distributed as elliptical family. So it's basically this kurtosis is equal to 0 when data comes from Gaussian distribution. And it also measures peakedness, so how concentrated your data is near 0 and how heavy-tailed that family is. And good news is that, in fact, if you can write that expression as a kurtosis of marginal variable divided by 1/3. Because this looks like it's not so easy to estimate, like how to construct this good estimator for that. But this helps a lot, so this is something that we will use. So if you're in the family of elliptical distribution, then we know what is the optimal shrinkage parameter. So how much do we shrink? How much? So beta naught, remember, is the degree of belief in the sample covariance matrix. And we have an expression for it, which just depends on those two parameters. So the sphericity and the kurtosis. So if we are able to estimate those, obviously we have a good estimator for that degree of belief on the sample covariance matrix. And how this result is derived is basically, I give some details here, but I will skip it. You can read it from the paper, which is on arXiv. So we have quite neat, easy formula for that optimal shrinkage, but now we need to estimate that those parameters. So basically, this was the estimator. So basically, we have estimator for the sphericity, gamma hat, and the kurtosis kappa hat. Then we have estimator for that shrinkage factor. And kappa hat, as I told earlier, is very easy to estimate. You can just compute sample kurtosis of the marginal variables and take the average of those, and then just divide that by 1/3, and you get an estimate of that. So that part of the problem is easy. Then there's another estimator for sphericity that was proposed earlier by Chang and Wiesel, which says that first compute a different matrix called the sign covariance matrix. And then if you compute this statistic, then that statistic is consistent estimator of that sphericity under the random matrix theory regime. So which is the case when P and N, so the dimension and the sample length, goes to infinity at the same rate. So under this random matrix theory regime, which is actually the regime that we are interested in, because we don't believe that we have a lot of samples, and even if we would have a lot of samples, then maybe you don't really need regularization like this. So that's one estimator. Then we propose another sphericity estimator, which is given here. It looks tiny bit more complicated. It's based on the sample covariance matrix, actually the trace. So what are those? So for example here, the first part here is the mean of the squared sample eigenvalues. And the next statistic there that has squared sign is the mean of the sample eigenvalues. And then you just scale them properly. And when you do that, and then there's some factors here, And the important thing is here that if you have a lot of sample length, n is large, then the statistic is basically equal to this, because these factors are equal to 1. And why are we interested in this is because this is unbiased estimator of the mean of the squared eigenvalues. And an immediate consequence of this is that if you take the mean of the sample squared eigenvalues of the sample covariance matrix, it's not a consistent estimator of the mean of the squared eigenvalues of the true covariance matrix. So this is something that, if you plug in, you would think that holds true, and you use that as your estimator, but it's not a consistent. So actually you need this here, in order to have a consistent estimator of the mean of the squared eigenvalues. So since this sphericity measure was given as follows, we now have an estimator of that statistic. So we now have two sphericity statistics that we can use, and we get two estimators of beta, and those were those red and blue lines that I showed earlier. So now I'm going to go to another applications where we can use these estimators. So in the first part of the talk, we use these estimators in portfolio allocation. And another application that I want to talk is the microarray data analysis, where you can also use these estimators. And this is the case exactly where you have very large dimension, but your sample length is very small. So look at here, for example, there are a lot of data sets available, and here you have 16,000, because the dimension is number of genes. So you can have 16,000 genes, but your samples are only 190. So there's really a case where you really have to be careful, like how, if you want to estimate the covariance matrix, then you definitely need some regularization here. So what is the idea? It's actually a classification problem where you have, for example, different classes of, for example, subtypes of cancer. And there's a training data where you know which subtype cancer class the microarray measurement belongs to. And you try to use that training data to build a classifier so that you would use minimum number of genes. So you would like to identify which genes influence the trait. So it's not just doing a good classification as we would like to, but it would also, you would like to do some selection of the genes at the same time. And that's exactly what we try to do, try to achieve is that we do accurate classification, but at the same time we reduce so basically these genes are the features in this problem. So you would like to pin out which genes are important in the classification. So you would like to have ideally exactly something like this. So there are some benchmark methods, for example, these two that are quite well known. And we propose another approach that can be used in this kind of context where your sample length is very small, but your dimension is very large. So this gives kind of a good framework where we can use our method. And it's quite simple. So you compute, so we use a linear classifier. So we compute the scores for each class. They are linear in the data. And we choose that the beta hat gives the coefficients for on the linear combination. So if we want to choose some genes, we would like some of the coefficients to be 0. And we would like them to be 0 simultaneously for each score. And if we do that, then you would have a situation that is given here. And to achieve that, we use this idea that those weights are computed as follows. We use a hard thresholding operator, which sets some of the rows equal to 0, so that we do the gene selection at the same time as we do classification. So that is the main idea. So we need to estimate the covariance matrix, and we use the previous L2 estimator, which used that statistic that I showed in the previous slide. And then we use Q norm to decide which rows do we set to 0. And the default choice that we use is infinity norm, because that seems to work the best. And here are examples on those 3 data sets that I just showed you. So these last 2 are our method. And then there's a bunch of machine learning classifiers that we tested against. And you can see there's random forest, there are the shrunken centroid method that I mentioned, and other. And you can see there these 2 on the left are our method. And you can see that the classification error is very small for our method, but other methods has higher. And you can also see that the genes that we select is also, the number of genes we select when we do the classification is also very small. So those are those dots, squares, and bullets, and triangles. So what is good if we compare to this other method? The good thing of this is simplicity, because this is very fast to compute. If you run with other methods, they take really long time. They have R packages out there at C-run, but it takes really long time to do the classification. But it takes just a second to do ours, even in this kind of data set. It does accurate classification if you compare, because you see here it's among the best here with this guy. It's the best, almost the best, but we do good gene selection. There it is clearly the best. So it's very fast to compute. It's among the best, and it does. It chooses a very small amount of genes when you do that. So that's something that a specialist would need. Look at that information, what genes were chosen. So basically that was my talk. So this talk was about covariance matrix estimation in high dimension, and in the case that the sample length is not that big compared to your dimension, and something about some applications where it can be used, like portfolio allocation, which is actually in finance a topic that there's really a lot of papers on covariance estimation in finance, which probably people in machine learning don't know about, but that's an important topic there. And then there's a topic that is in genomic studies quite often used.